A quadric surface, not to be confused with a quartic surface, a term I accidentally use sometimes, is a second degree equation with three variables. The general form looks like this: ax squared, by squared, cz squared, dxy, exz, fyz, gx, hy, iz, j equals 0. Basically any combination of the variables to any degree, at most 2, with the exception of x, y, z together, because then that wouldn't be at most 2. But that is the general form of a quadric surface. But the problem is I mean, you can write something like that, but generally speaking, we can use some algebra to rearrange these equations into 6 basic types. And they're the ellipsoid, the hyperboloid of one sheet, the hyperboloid of 2 sheets, elliptic cones, elliptic paraboloids, and hyperbolic paraboloids. Now, you'll notice that these have a lot more reduced terms than that, and those generally have to do with the fact that if you work it just right, you should be able to separate them in such a way that they're either rotations of one of these forms or translations. So they have maybe a shifted origin or a rotated origin. But generally speaking, with a little bit of algebra, you can set up everything into one of these 6 archetypes. So I'm going to go through each one and talk about where they come from. The ellipsoid is the most straightforward. It looks like the equation of an ellipse, except it's for 3 variables instead of 2. And what that basically says is that if I don't consider x, I have an ellipse. If I don't consider y, I have an ellipse, and so on and so forth. Now for the hyperboloid, what I see is if I don't consider z, I have an ellipse. But if I don't consider x, I have what looks like a hyperbola. And if I don't consider y, I have what also looks like a hyperbola. And so that's going to create what we're going to find as a hyperboloid. And we'll show in examples what that looks like. The hyperboloid of 2 sheets says that I can't construct the ellipse as designed if I just don't consider z. There's a way to do it, but you have to be more careful. But generally speaking, if I don't consider y or don't consider x, I have a hyperbola outside the gate. So for an elliptic cone, what you find is this is equal to 0. So instead of, in the case of the hyperboloid, it being equal to 1, it's actually equal to 0. And what that allows you to do is to say z equals something. So if I don't consider x, this is going to be very close to like a z equals y with some plus or minuses on the square root, and z equals x. And so you're going to have these lines that go through the origin. And then if you set z equal to a value, you're going to have something that looks like an ellipse. So you're going to have these cones, but instead of being circular cones, they're elliptical cones. So for the elliptic paraboloid, instead of being like z equals y, with a little bit of change there, it's more like z equals y squared or z equals x squared if we don't consider. So you have these parabolas that come out, and they're chained together with these ellipses. And finally, you have a hyperbolic paraboloid, which has the same type of behavior, except that instead of ellipses, they're parabolas they're hyperbolas that connect them. And so the problem with that is that, whereas an ellipse has that nice ring, the hyperbolas go out like this. So if they swap, if it goes from this to that, you're going to see this interesting saddle piece start to have this nice shift. You have a big state shift at z for positive values and z for negative values, because that's going to kind of flip that equation. So we're going to plot examples here, but I want to point out that these are best graphed by piecing together what are known as cross sections. So what you can think of like projections in the plane, where I say, z is equal to, in this case, z is equal to 0. So what does it look like when z is 0? Or what does it look like when z is 1 or z is 2? And by getting those cross sections, you can kind of stitch them together and create a picture. So we can set z equal to 0, we can set x equal to 0, we can set z equal to 1. By doing that, you're going to get a lot of different pictures, and those put together are going to give you a better understanding of what you're looking at in 3 dimensions.